Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on aside as we jump into the final section in Chapter 6 in the Big Ideas Math Integrated Math 1 textbook. This is Section 6.6 on recursively defined sequences. Now, it looks like on the first page alone that this covers both geometric and arithmetic sequences. Maybe more geometric because we're still under the exponential functions chapter, but it looks like this chapter as well is just hitting more things on just sequences, and it's like, hey, let's hit the arithmetic things as well. So recursively defined sequences, it's going to look weird, but what it is doing is something that you probably think about more so than you know. You'll see what I mean when we actually talk about them here in a second. Jump to the description section down below if you'd like to download the PDF of this thing, as well as a graph paper if we have to plot graphs, points on graphs, and as well as the problem set. The timestamps are down below as well. I'm going to begin with the lecture portion. Without further ado, I'm going to go ahead and get started. We have 4 bullet points to cover: writing terms of recursively defined sequences, so come up with the next ones, maybe something based off the rule, but write the rules as well. What is that? It's called a recursive rule. Instead of before, what I stated was an explicit rule. This is the recursive rule. We're going to translate between recursive and explicit rules. Okay, they're actually saying the word here. In fact, this is where it's in your vocab. So you've probably heard me say this phrase over and over again. That's what we've been doing before when they said write the function with the n in it, the n-1 thing. Those were explicit rules. We have recursive rules. They'll also include some form of n-1, but in a totally different way. And write recursive rules for special sequences. I wonder if that's like the Fibonacci sequence and things like that. Things that aren't necessarily arithmetic nor geometric. So depends on what it is. We'll take a look. So far in this book, you've defined arithmetic and geometric sequences explicitly as an explicit rule gives a sub n as a function of the term's position number n. So what they mean is we actually use the position number to calculate its value. If I want to find the 100th term, I actually substitute 100 in my calculation to get my value. So when we have this 3, 5, 7, 9 arithmetic sequence here, our explicit rule for this would have been first term plus common difference times n-1, if you remember that. And we would simplify that by distributing the 2 into these and then combining like terms. We could also write it as 2n plus 1. Whatever these things were, if I wanted to find the 100th term, I would substitute 100 in for n. 2 times 100 plus 1 is 201. And that's what explicit rules are good for. Now, recursive rules are good for something else, or at least recursive thought, which is, like I said, what you guys probably almost always do. And when I say you guys, I mean everybody. I don't mean just, you, me, whatever. Everybody thinks this way. You will define arithmetic and geometric sequences recursively. A recursive rule gives the beginning term or terms of a sequence and a recursive equation that tells how it's related to one or more preceding terms. What the recursive rule thing means to me is how do you get the next term from the term before it? So whenever I give you a sequence like this one right here, I'd say, hey guys, tell me what the pattern is. You know what most people would say? They'd say add 2. They'd say plus 2, plus 2, plus 2. Which means 9 plus 2 is 11. 11 plus 2 is 13. 13 plus 2. That's recursion, using the previous term to get the next term. So if I wanted to find the 100th term using recursion, I would need to know the 99th term. If I knew the 99th term was 199, then you add 2 to that one. So that's kind of what recursion is. That's the easy part about it. The hard part is the part where people have trouble coming up with the appearance of the formula, and they're right here. The recursive equation for arithmetic sequence and geometric sequence are right here. A sub n equals a sub n minus 1 plus d, and a sub n equals r times a sub n minus 1. Now the n minus 1s this time are inside the subscripts of this notation, and it's good that we're probably using subscript notation itself as opposed to function notation, because this would look kind of weird for us. F of n equals f of n minus 1 plus d. Actually, yeah, I suppose you could still use it. And who knows, maybe they'll use them as well. R times f of n minus 1. The reason why you might not want to use this is because you might confuse it with what we were doing up here. See where it says 2 times n minus 1? This is actually multiplication. This is not multiplication. This is function notation. And that's why that might get a little confusing here. So what these things are saying is to find the value of some term, take the value of the term before it, and add your common difference. To find the value of some term, take the value of the term before it and multiply its common ratio. That's what those two things mean as far as recursion goes. Now, the thing on recursion is, if I said, hey, what's this rule? You say plus 2, plus 2, plus 2. You ain't wrong, but it's a little incomplete. If I said, guys, make a list where you're adding 2 each time, will everyone come up with this exact list? No, you need to tell someone where you start from. So we starting from 3, add 2 over and over to make a list. Now everyone would make the same list, assuming they add 2 correctly to it. So what we also have to do in our rules is we have to note what the first term is, or some term is in it. So in these ones, they say write the first 6 terms of each sequence, then graph each sequence. This first example says the value of your first term is 2, and then the recursively defined rule for this, what appears to be an arithmetic sequence, is we're going to add 3 from the previous term. Now they do this very exhaustively here. I might do it exhaustively the first time out for both of them, but they're saying the first term is 2. The second term, you take the first term and add 3. So you do 2 plus 3 to get 5. The third term, you take the second term plus 3. So you take 5 plus 3 to get 8. So you have to get that next term to get you have to get some term to get the term after it. The fourth term takes the third term plus 3, which is 8 plus 3. The fifth term is the fourth term plus 3, which is 11 plus 3. And the sixth term is the fifth term plus 3, which is 14 plus 3. It says write the first 6 terms, and there you have a sub 1 to a sub 6 right there, these 6 guys right here. Now, it's probably significantly easier to just say plus 3, plus 3, plus 3. And that's what I'm going to do in the future after maybe one set of problems with them. And that's where, again, it can look confusing, but we do it probably a lot easier than it looks. Plot the points, don't connect the dots, it's still a sequence. In this one, the first term is 1, and then you follow this rule. It says 3 times a sub n minus 1. So here you are taking your previous term and multiplying by 3. If the first term is 1, the next term is 3 times 1, which is 3. Next term is 3 times the second term, which is 9. Fourth term is 3 times the third term. 3 times 9 is 27. And so on and so on. You keep multiplying. These are powers of 3. And you get that. And we've seen some of these graphs before. They get a little squished at the bottom as they go pretty huge later. Okay. Let's write recursive rules. Let's say we have a pattern and we have to come up with that rule. So coming up with the rule, again, let's indicate what the first term is. Make sure to write that in your sequence itself, and then describe what happens each time as you go along. Now you have to note whether you're doing arithmetic or geometric, obviously. Is there a common difference or common ratio? In the first one, there appears to be a common difference where you're adding 12 each time. I don't know if you recognize it early on, but 6 plus 12 is 18, and you can check the rest of them. They're adding 12. So you're adding 12 each time. So for this rule, to get the next term, you take the term before it and add 12. Take the term before it and add 12. And that's what they're writing right here. Now, the other thing you're going to have to note, however, is the value of the first term. Don't forget it. The first term is negative 30. So they state as an answer, first term is negative 30, and then to get the next term, you add 12. Sometimes I'll write it at the end. I'll say, oh, and by the way, the first term is negative 30. Apologies if I do it after the fact. I do that by habit. And although I'm consciously aware of the fact that I'll be doing it here, I'm probably going to still do that. We'll see. The next one appears to be geometric in nature. You're dividing by 5, right? Well, we actually have to say multiplying by 5, right? What the common ratio is. So take the previous term, multiplying by 1/5. Take the previous term, multiply by 1/5, 1/5, 1/5 as you keep progressing forward. So they show that times 1/5 or times 0.2, 0.2. But you have to indicate the first term as well. First term is 500 with that common ratio. So they're going to write it like that, with the first term being 500. Take the term before it and multiply by 1/5 to get the new term, like that. So when we write our rules, it's not just this portion that we write out. We also write out what the first term is to indicate that for somebody. They have some word problem ones down there. I'll leave it for whatever they give us later. Translating between recursive and explicit rules. If you notice, both of them each use the value of the first term and the common ratio, or value of the first term and the common difference. So it's not necessarily too hard to do with that in mind. They say write an explicit rule given these recursive rules. Pull out the information that you have. Literally, this is the first term. And this here is the common difference. Note that it is negative. First term 25, common difference negative 10. If you recall how these things work, this goes actually back a previous chapter or two. I forget when we did arithmetic sequences, but this goes back to our arithmetic sequence chapter. Now, I like to put the D in front right there, so negative 10 like that, personally. So you'll see me do it that way. But the first term plus your common difference times n minus 1. First term plus common difference times n minus 1. They distribute and combine like terms. So here's the explicit rule here. So there's nothing necessarily different that we're doing. We're just noting how the recursive rule is written out, pulling out the information, first term and common difference, and then writing them in as we always did. This one here, first term and common ratio. That common ratio is negative 0.5, and we just came off of geometric sequences in their explicit rule. The formula looks like this. Take the first term times the common ratio to the n minus 1 power. First term here was 19.6, common ratio negative 0.5, place it in parentheses, please, and raise to the n minus 1 power like so. There's your explicit rule. We can go the other way as well. You just got to pull out the information. Now, this one is going to be a little bit different because if they use this as the explicit rule for an arithmetic sequence, this doesn't feature n minus 1 on it. So 3 is not the first term. In fact, it's the 0th term. If you substitute 0 in for n, you actually get negative 3. But if you substitute 1 for n, you'll get your first term. You actually just take the 3 and you subtract 2 once. You can see that negative 2 times 1 plus 3 is 1. That's your first term. So that's the one tricky part about this, is because this is a simplified version of that rule, it doesn't appear to be in this format where the first term 1 is written there, and then they have it, again, they have it simplified. Substitute in 1 to get the first term, and your common difference is indeed negative 2, the number that's multiplying by n. So with those two things in mind, we can write out our rule. Obviously, we just write out that the first term is 1 as we would before, and take the previous term and subtract 2 from it to get the value of the next term like so. Part B is written straight up point blank where the n minus 1 is present here. So negative 3 actually is your first term and 2 is your common ratio. So when we write this out, we'll write a sub 1 equals negative 3. That is down here. And then you take 2, your common ratio, multiply it by the previous term to get the value of the next term. That's the answer there. So just pulling out the information based on what's there. You can try and substitute 1 to make sure that you have the right value. It looks like they just stayed up straight at the first term. Stayed up straight. They straight up state that the first term is negative 3 because they're aware of the appearance of the formula being what it is. Is that it? Is that it? Is that? Nope, there's still more. Oh, special sequences. That's right. So they use, oh, hey, here's the Fibonacci sequence. This is the one that, if you were with me, I brought it up before. This thing actually appears in a Fibonacci sequence. I won't really explain why. But, I should have capitalized the F when I wrote it out that one time. But the Fibonacci sequence occurs in nature. There's a spiral set to them. I'm not going to explain it right now. But you can write recursive rules for things that are neither arithmetic nor geometric. And we've actually seen a couple of them. We just haven't written rules for them. But one of the examples is shown here in the Fibonacci sequence. And I've mentioned this before, and I'll do it again right here. You take two terms that add together, and you'll get the value of the next term. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, etc. The next term would be 5 plus 8, which is 13. So that would continue. So how do we write a recursive rule from that? It seems to be, to find the value of some next term, it seems to take the value of the two terms before it. So if a sub n minus 1 is the value of the term before it, then a sub n minus 2 is the value two terms before it. So if I want to write out a sequence from here, well, they're showing some stuff on the difference of two terms is something, something. But I already explained how the sequence actually goes. But it's not arithmetic nor geometric. There's no common ratio nor common difference. But you do notice that you take the value of any two terms to get the value of the next term. The first two terms added together gets the third. The second and third term gets the fourth. The third and fourth gets the fifth. Fourth and fifth gets the sixth, etc. So you take the two previous terms, the value of two terms before plus the value of the term before, and then you get the value of the next term. And that's how the recursive rule can show up here. That's literally what we would write for that answer. So they might give us some tricky ones. I'll see if I can explain it as best as possible to get what we get there. Now, we do note what the first two terms are, right? The final answer actually, I guess, will be this one because we have to state what both of the first two terms are for this to work out. Now, they said find the next three terms. For me, literally, I'll just take, 5 plus 8, like I said, gets us 13. 8 plus 13 would give us 21, and 13 plus 21 would give us 34. So I did use the Fibonacci sequence in the previous section. I don't remember what question it was on, but you might be able to find it. Okay, that's the end of the lecture portion. Let's now go to the vocabulary and core concept check, numbers 1 and 2. We're going up to problem number 59 in this set, I believe it is. Number 1, complete the sentence. A recursive rule gives the beginning terms of a sequence and a blank that tells how this is related to one or more preceding terms. Gives the beginning term or terms of a sequence and I want to say common difference or ratio. I don't know specifically if that's going to be the answer, but I'll say common difference or ratio. Because it depends on whether it's arithmetic or geometric. That tells how it's related to it. So you have to apply that rule there. Okay, which one doesn't belong? Which rule does not belong with the other three? Explain your reasoning. These three are recursive rules. and this is an explicit rule. Now, I've been again saying the phrase explicit rule over and over before, but these ones are recursive, yes, explicit. You can tell just based off the fact that these ones use the a sub n minus 1. This one does not. This is based on n, based on the position of the term. The other ones are based off the value of the previous term. So hopefully the first one's right when I say exactly what that one was, if you have to fill it out, but hopefully at least you understood why I stated what I stated. Okay, we're going to do problems numbers 3 through 59. I'm going to go ahead and get started. In exercises 3 through 6, determine whether the recursive rule represents an arithmetic or geometric sequence. So these are written as the rules themselves. This is really just based on, is your a sub n minus 1 being multiplied by something, or is it adding with something? Or I guess subtracting as well. Because this one's multiplying with something, 7 times a sub n minus 1, this is going to be a geometric sequence because it has a common ratio of 7. That's what's multiplying there. Number 4, the first term, and we're not doing anything else with these. They're just giving you exposure to the appearance of the rules, and then we can determine what we do with them afterward, right? So the first term here is 18, and then you take the 18 to get the value of the second term by adding 1 to it. Adding 1 to this thing means this will be an arithmetic sequence that has a common difference of 1. Number 5, we have as well a common difference, but this time it's not 4, it's negative 4. If you're subtracting 4 each time, that is still a common difference regardless, which means this one too will be an arithmetic sequence. A sub n minus 1 plus negative 4 or minus 4. This is once again arithmetic. I'm fully expecting geometric on the next one. Or is there a neither case? No, this is just geometric. Number 6, we have another geometric sequence. Keep in mind you can multiply by negatives. It'll still be geometric. The signs will just change. You can even multiply by fractions, less than 1. It'll make the number smaller. That's not the case here, but it is geometric. There's a common ratio of negative 6. Okay, so there are the first 4. Let's go to numbers 7 through 12, where you write the first 6 terms of the sequence and then graph the sequence. So I'll make sure to have my graph paper stuff ready momentarily. I just hit the copy button. We'll see if it carried over. So the first problem here on number 7, I'm going to go a little bit more slowly on, the same way that the lecture version did. After this, I will not go all that slowly, all depending. So the rule is here, right? We have a sub 1 is 0, and the next term, you take the term before it and add 2. So like the second term, you take a sub 2 minus 1, which is a sub 1, and you add 2 to it. A sub 1 is 0, and 0 plus 2 gives you 2. So that's the second term. They said to write the first 6 terms. So we have terms 1 and 2. Term 3 takes the second term and adds 2 to it, and the second term is 2. And you add that and get 4. Remember, the plus 2 is the rule that I'm using with this each time. The fourth term takes the third term and adds 2, which is 4 plus 2 to get 6. The fifth term takes the fourth term and adds 2 to it, which is 6 plus 2, which is 8. And the sixth term, my A's are getting really weird looking now, is the fifth term plus 2, which is 8 plus 2, or 10. So like I said, I know that's the long route of this thing. First term 0, etc. And they go down right there. So we're looking at these. We're going to go ahead and graph them. This can be easily graphed for this set. Let's see if it actually copied. It did. So 0, 2, 4, 6, 8, 10. Those are on 1, 2, 3, 4, 5, and 6. 0, 2, 4, 6, 8, 10. Arithmetic, which means a linear nature to it. And that should be our final complete answer. Remember, we start at the first term, so that's at n equals 1. Okay, number 8, I'm going to go more quickly on because it's yet another arithmetic sequence. We can tell by the common difference of negative 5. Let's write out the rule to begin with. We're going to start with the first term of 10, and then we get other terms by subtracting 5 from them. So a sub 2, I'll go slightly quicker on this one, is 10 minus 5, which is 5. The third term is 5 minus 5, which is 0. The fourth term is 0 minus 5, which is negative 5. The fifth term is negative 5 minus 5, which is negative 10. And the sixth term is negative 10 minus 5, which is negative 15. So we're looking at all those terms there. Shoot, I wish I had the tall graph paper to use this time. I guess I'll just scale this by 2s this time. So on this one, we'll go 10 and 20, like so. And we're going to start at 10 on the first term, and then it goes down by 5s each time. So 10, and then 5 is halfway in between like that, and then 0, and then -5, -10, -15. So also linear nature being an arithmetic sequence. Okay, number 9 is a geometric sequence. We can tell based off of that common ratio, multiplying by 3 each time to get from one term to the next. Now we're starting on 2 as our first term. So I'll slow this one down as well. I'll go on that longer version of what we had. So the second term takes 3 times the first term, or 3 times 2, which gives us 6. The third term takes 3 times the second term, which is 3 times 6, or 18. The fourth term is 3 times the third term, which is 3 times 18, or 54. The fifth term is 3 times the fourth term, or 3 times 54, which is 162. And the sixth term, oh, my A's get really weird at the end, is 3 times the fifth term, or 3 times 162, which is 486. 486. So we're going to plot these ones here. This is where it's going to be having a squished bottom, given that we have to go up to basically 500. And let's do what we can on that. So a little copy paste. Didn't hurt nobody. Let's go up. Yeah, let's go up to 500. Here, 500, which means this is 400, 300, 200, and 100. Let's maybe start from the top, make it a little easier looking. The sixth term is all the way over here where we get 486, really close to 500. This is 450, 460, 470, 480, somewhere near there. So 486, boom. Now 162 already goes pretty small there. So 5 and 162, a little more than 150, maybe up right here. 54, really close to 50, just above it. Now we're getting Smallville. 18. 2/5 of the way up to 50, just about. And 6 and 2. I mean, can you even tell what these guys will be? So there they are. Again, it has the exponential curve appearance. And you're going to see a lot of those for these kinds of problems. Number 10. Also a geometric sequence given this common ratio. It does have a decimal of 1.5. I don't know if that'll hurt us, like haunt us in terms of like being decimals. We'll see. A sub n equals 1.5 times a sub n minus 1. So I'll go slightly quicker here. Second term is 1.5 times the first term of 8. 1.5 times 8 is 12. I'll do what I can without a calculator if I'm able to. 1.5 times 12 should be 18. Hopefully these are not decimals at all. 1.5 times 18 is 27. Oh, this next one will be a decimal. 40 and a half. So 1.5 times 27 is 40.5. I have one more to do. Can I get it in my head? 1.5 times 40.5. 60.75, I believe. 60.75. So, given those, again, boom, 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 boom. 60. Oh, dearest heavens. If we go by sixes, I don't know if that's too awkward, but 6, 12, 30. I don't know if going by sixes will be the best way to do it, but I'll try. Given that we have 8 there, from 6 to 12, 8 is 2/3 of the way there, so about 8 like that. I know, this will look weird, but this will just be my scale, okay? So I can fit things best as possible. 12 is right there, homie. 2 6s. And then 18 is at, well, it's 3 6s. So actually, that's not too bad. 27 is halfway between 24 and 30. Yeah, this panned out. 40.5 will be a weird one. 36, 42, hot hike, 40.5, sure, like that. And 60.75 just to tick above 60. Probably something like that right there. Okay, so there are the points. Not too bad. You can still see the exponential curve happening on that one for a geometric sequence. Now, We have two more geometric sequences at hand. I think at this point I'm going to go kind of on the significantly faster train. If you understand the appearance of what a recursive rule is telling you, just apply it to the way that you best know how. Meaning, take the previous term and multiply by negative 1/2. Heck, to us, to you, you might say, take the previous term and divide by negative 2. Or take the previous term, divide by 2, and change signs each time. We need the second term, third, fourth, fifth, and sixth. If I wanted to go super fast on this thing, I would say, this is negative, that's positive. This is negative, that's positive. This is negative. And then I divide them by 2. 80 divided by 2, 40 divided by 2, 20 divided by 2, 10 divided by 2, and 5 divided by 2. I'll just put negative 2.5 for that one. Or negative 5/2, right? It's an either or thing. But those are the next 6 terms. So you can still do it really quickly as long as you make sense of how that rule is going. Divide by negative 2, multiply by negative 1/2, right? But those are the 6 terms there. Now we still have to plot the points where, if that's 80, might as well just go up to 100 here. All these things end on like 10s anyway, so I think that makes most sense. So first term being 80. Oh, negative 40. Oh, shoot. Hold on. We have to go positive, negative, positive, negative. So let's see. Negative 50. Okay. So go 80 and then negative 40 down here for the second term. And then positive 20. And then negative 10. And then positive 5. Halfway between negative 2.5, about a quarter of the way. Voom, 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 voom. And you can see that oscillating pattern as it shrinks right there. Last one here, number 12. First term's negative 7, and we keep multiplying by negative 4, which means the numbers will get pretty big. They will also change signs as the previous one showed. So let's kind of keep it brief as we do it. The a sub n, also geometric, negative 4 times a sub n minus 1. Take the previous term times negative 4. So same thing when it comes to signs. They will change each time, but it started negative, so it'll go positive thereafter. So positive, negative, positive, negative, positive. Multiply them by 4. 7 times 4 is 28. 28 times 4, 112. 112 times 4, 448. 448 times 4, 450 times 4, 900, 1800 minus 1792. And I don't know that one times 4. I don't want to mess up. Let's see. 1800 times 4. I want to try it though. 36, 7200. 7168. Wait, not 7168. Wait. Yeah, 7168? Is that right? 7168. I think that's good based off what I was doing there. I don't really know. So, okay. We have those points. Now, that is a lot. I might even have to go by thousands at this point, right? I don't know what's going to be easiest or hardest here. I guess going up to 10,000 just might be the way to go here. Now, these are changing signs each time, so we will have to go up and down. This is not going to be very beneficial to find where negative 7 is, basically. Hope you ate with that. Okay, so I'm going to start with 7168 just to kind of reach high first. That's the 6th term. Now, this is 7,000. That's 8,000, so this is not quite all that high in general. It's just right there. Negative 1792 on the 5th term. Negative 2,000. Pretty close going down there. 448. That's less than 500. And 500 is already, like right there. So we're going to be pretty squished after this. There's no really good way to do this other than just say, hey, this just gets really small really fast. Negative 112, right? 28, yeah, super small. Negative 7, yeah, super small. So at some point, it just shrinks to nothingness. I don't know what their end game is with us seeing graphs that go so small like that. I wish they, multiplied by negative 2 instead and started from, negative 3. At least you get a little more out of that. All right, write a recursive rule for the sequences from 13 to 20. So 8 problems of probably different representations. You can see the first 2 being tables. Now, I'm just going to write out this list. This is 7, 16, 25, and 34. That is the first 4 terms. Now, the sequence probably continues after that. They're just showing the first 4. You can clearly see there's an addition of 9 each time, which means common difference of 9. You have a first term of 7 and common difference of 9. We are doing recursive rules. Now, the recursive rule will include writing out the first term, but to find the value of some next term, you take the term before it and you add 9 to it, noting that the first term is 7. Again, I write the first term on the bottom for whatever reason I do. I just do. But you have to note what the first term is, or some term. I would do the first. And then state what you're doing from thereafter. This was arithmetic. Number 14 does not appear arithmetic this time. I'm guessing it's really just going to be one or the other. So here our first term is 8, and then 24, 72, and 216. You can see we're multiplying by 3 to begin with. The question is, does it continue doing that? And yeah, 24 times 3 is 72. 72 times 3 is indeed 216. So, multiplying by 3 each time, you do have a first term of 8 and a common ratio of 3. So from there, you take the term before and multiply by your common ratio. So like that, noting that our first term is 8. Like so. Okay, number 15. Speaking of geometric sequences, we are dividing by 3, but we don't quite say dividing by 3 here. Maybe you couldn't tell from the beginning ones, but you can see we're going from 27 to 9 to 3. Those are pretty more straightforward. But hey, we're multiplying by 1/3. Times 1/3. So I'll just kind of indicate that here, times 1/3. So from there, we could probably just write out our rule, right? We say we take 1/3 of the previous term, and our first term being 243, like that. Number 16. Looks like we're adding 8 each time, and our first term being 3 means we can write this recursive rule just fine. So plus 8 from one term to the next, that's our common difference. So our rule is we take the term before and add 8 to it. Our first term was 3. Still 4 more in the fray here. 2 more lists and then 2 graphs. Okay, so for this one, I'll go straight into the rule. You can tell there's a subtraction of 3. This time I'll write it the way that the book does it. They start from the first term, indicate that it's 0, and then the value of the next term takes the value of the term before it and subtracts 3 from it. Let me get some water. Feeling kind of sharp pain in my throat. Okay. Okay. Number 18, we're multiplying by -4. You can tell by the sign change on that one. So the first term is 5, but then you multiply by -4 to get the next term. So -4 times the previous term, like that. Okay. Number 19 is a graph. Look at where the numbers indicate. We got to look at the y values here. So the first term is -1, second term is -4, etc. Looks a little weird because where they write the ordered pairs, but -1, then -4, then -16, then -64, and it would continue. Now, last time we were multiplying by -4, starting from 5. We're not multiplying by a negative this time. The numbers stay negative. They started negative, right? So your first term is -1, and then you're multiplying by 4 each time, but not -4. 4 times a sub n minus 1. Also geometric, by the way. This was a geometric sequence given that rule. And then number 20 appears linear, which means, arithmetic. And this one has a first term of 35. And it looks like we're subtracting 11 each time. So 35, 24, 13, and 2. And then it goes to negative land because, hey, we're subtracting 11 starting from 35. So a sub n is a sub n minus 1 minus 11. Okay. Number 21. Write a recursive rule for the number of bacterial cells over time. As you can tell, the cells are doubling over time. In the first hour, there is 1, so that is your first term, if you will. So on number 21, we can write it as the number of cells over time. Oh, the only question is, are we doing... I guess it's how many cells there are. I guess the cell is splitting. It's not getting 2 new bacterial cells. It's splitting itself apart. So there's 1, and then there are 2, and then there are 4, and then there are 8. So we got to write a recursive rule there. We're doubling each time. So a sub n is doubling a sub n minus 1, the previous term, starting from 1. In the first hour, there is 1. On number 22, it says write a recursive rule for the length of the deer antler over time. This is based on number of days. So on the first day is the first term. We have 4.5 inches. Ooh, I don't like the, I'm going to write 4.5. 4.5 and then 4.75 inches and then 5 inches and then 5.25 inches. I'd rather almost write improper fraction versions. I'm not a mixed number guy. I don't know why. Anyway, we're adding 0.25 each time, which means we're adding a quarter. I'll just write it as common difference as 1/4 because it started off as a fraction, so I'll leave it that way. So to find the value of the next term, you take the value of the previous term and you add 1/4 to it, like so. You add a 1/4. Not multiply by a 1/4, but you add a 1/4 of an inch. You start with 4.5 inches. I'll still write that as 4.5. Okay. Numbers 23 to 28, write an explicit rule for the recursive rule. So once again, you can tell, guys, they're doing both arithmetic and geometric on all of these things. So, we good. So we're writing the explicit rule. Keep in mind that it uses the uses n minus 1, but in a different way. So this one is an arithmetic sequence. You can tell because the common difference here. So your first term is -3. That's already noted. Your common difference is 3. So boom and boom. How do we write an explicit rule based off that? Well, its appearance is you take your first term -3 and you add 3n minus 1 times. Now this in and of itself would be a fine answer, but they tend to do a lot of simplification of these. So we distribute the 3 into this. So 3n minus 3. And -3 minus 3 is -6. So we get 3n minus 6. Here's your explicit rule for the arithmetic sequence at hand. Number 24 is also an arithmetic sequence. They tell you the first term. Now, if you have trouble going from this rule to the other rule, maybe you have better luck in writing out your list first and then coming up with the rule. I don't know. This seems to be good enough for me. Your -12 is your common difference, this time, with your first term being 8. So we can write it based off that. You take the first term and you subtract 12, n minus 1 times. Distribute the -12 into there. Given that they have those numbers straight up, I think it's probably easiest to just come straight off of it like that. 8 plus 12 is 20, and you have -12n plus 20. So we are, again, revisiting, right? I stated this before. This part's coming from a previous chapter. Arithmetic sequence, explicit rules. That's not new. The new part is coming off of a different appearance of a recursive equation and doing it. So this is not all on exponential functions, at least not the first two. This next one looks like it will be. Number 25 is a geometric sequence because of the multiplication, the common ratio. So a sub 1 is 16, and a sub n, you take 0.5 times the previous term, a sub n minus 1. So that means we have a common ratio of 0.5, and your geometric sequence explicit rule, which we were writing all in the last section, you take your first term, 16, multiply by your common ratio here, n minus 1 times, and we're just going to leave it like that. We don't really do a distribution of that 0.5 or anything like that. We'll leave it as such. At least they've been doing that. There is another version of this where you can find the term before it and, write it out just to the nth power. They don't seem to want to do that, and I'm comfortable with it. Sometimes it's not really good to do it because in a case like this one here, you'd end up with a decimal for your 0th term because you'd have to divide 9 by -2. No, excuse me, -2 by 9. You have to divide -2 by 9. Because 9 is your common ratio. And yes, this is your R value. So given you have your first term there, we can write our rule based off the first term times the common ratio, n minus 1 times like so. Doesn't really get any simpler than that. Number 27, we have an addition of 17, starting from 4. So that's your common difference. It is an arithmetic sequence. So we are going to start from 4 and add 17 n minus 1 times. Distribute our 17. And do 4 minus 17, which is negative 13. So 17n minus 13. And then the last one from this set, I'll just write down below. We have a common ratio of negative 5, and we start from positive 5. But because I did say common ratio, this is indeed a geometric sequence. So its explicit rule has that exponent involved. So negative 5 times a sub n minus 1. Do put the negative 5 in parentheses, please, when we do this. A sub n is the first term times the common ratio to the n minus 1 power. So these both use n minus 1s, and they're little n minus 1s, but this is a subscript, this is a superscript, an exponent. Two totally different meanings here. This is raising to this power. This is just the version of that value. The value of the term before the nth term. Still might look a little confusing, but I hope that the work that we're doing is panning out. Okay, now we're going to write a recursive rule for the explicit rule. So number 29, pretty straightforward because it comes straight off of that geometric sequence explicit rule appearance. 7 is the first term, 3 is the common ratio. So a sub 1 is 7, and r is 3. So we can write the rule based off how we did before when they were lists. We could say, to take the previous term and multiply it by 3, starting from 7. I know I already noted 7, but I'm going to be doing it a second time. Now 30 is a little bit trickier because it is an arithmetic sequence, but more so its explicit rule is simplified. That means that although I am looking at right now the common difference in negative 4, yes, the number multiplied by n indicates how many what you do to your values there. So that is your d value. Let me write it down below actually. Common difference is negative 4. Your first term, you actually have to substitute 1 into here to figure out what it is. Negative 4 plus 2. Really, it's 2 minus 4. 2 being the 0th term, you subtract 4 from it once, you get negative 2, and that's the appearance it'll take on. So the value of the nth term, you take the value, take the value of the term before it, and you're subtracting 4 from it. And your first term is negative 2. Not 2, but negative 2. Okay. Number 31 is once again an arithmetic sequence. We have a sub n equals 1.5 n plus 3. So this once again is your common difference. Now your a sub 1, you're doing 3 plus 1.5. And I'm bringing this up in this way to just remind you of really what's going on here. 1.5 times 1 is 1.5. And I bring up the 3 first because I like to think of the 1.5 as your common difference. You do this to your number. So 4.5 is your first term. So I can write that as a sub n is a sub n minus 1 plus 1.5. And your first term being 4.5. So maybe we can use that moving forward for this next problem in understanding what exactly is going on. You know, when you write out your list, you go from negative 20 and add 6 each time, but negative 20 is not the first term, it's the 0th term. So 6n minus 20. So as far as your list goes, right, here's this like negative 20 right here, plus 6, that common difference, and plus 6, etc. So negative 14 is your first term, and 6 is your common difference. So here we're going to state that a sub 1 is negative 14. This time I'm writing it their way. A sub n is a sub n minus 1 plus 6. So however it is you want to go about it, whether you're substituting 1 into your actual equation to figure it out, or you're understanding how this list is simplified and how that works out, is up to you. Now, they didn't write any with that n minus 1 in mind on the arithmetics. They do them only for the geometrics. But if they did, if they started off by writing here negative 14 plus 6 times n minus 1 straight up, that is your first term. So you wouldn't have to do anything there. You could plug in 1, but don't add another 6 on top of it to get the first term. Because these ones, for example, are already in that form. So this is negative 5 to the n minus 1 power. Notice there is no number written in front. That would be a 1, and that would be your first term. So your first term is 1, and then you are taking negative 5 times the previous term to get the value of the next term. This is an explicit rule, or this is a geometric sequence from the explicit rule to the recursive rule. We have it. Number 34 is also a geometric sequence. Your first term is written plain as day. Your common ratio is written plain as day. Big or fraction-y as they are, we can kind of just copy paste. So negative 81 times 2/3 to the n minus 1 power. Your first term, negative 81, common ratio of 2/3. So negative 81, let's start from there. And then here's the problem, my commas look like my ones. A sub n is 2/3 times a sub n minus 1. Make sure that minus 1 is written small in the subscript there. Don't be putting like a minus 1 like that. That's not what we're doing. Let me fix that one though. Okay. Okay. In 35 to 38, we are going to graph the first 4 terms of the sequence with the description, and then we're going to write both a recursive and explicit rule. So a lot of things being had there. If do I paste? Do I get a graph if I paste? I do. So on the number 35, the first term of a sequence is 5. Each term of the sequence is 15 more than the preceding term. This is something where I wouldn't mind writing out the list first anyway. So 15 more than this is 20, plus 15 is 35, plus 15 is 50. That way I know what my scale is going to be after that. So they do say graph the first 4 terms. If I'm going up to 50, then I'm going to go up by 5s basically here. So 50, and this is 25 there. So these should fit. First term is 5, and plus 15, boom, boom, boom. So kind of up 3 over 1, if you will, on these ones. There's the graph. Our explicit and recursive rules can also be written. I'll try and fit them on the side here. So let's go. Which one should I do first here? They say write recursive and explicit. Let's start with recursive. So a sub n is a sub n minus 1 plus 15, and a sub 1 is 5. So you're starting from there. There's the recursive rule. The explicit rule, you take the first term and add 15 n minus 1 times. We distribute the 15 into there. Otherwise, that answer is fine. And now you have 15n minus 10. So here's our recursive rule and our explicit rule for those two. A lot to do on those problems, but I'll kind of try and streamline them as much as possible. Number 36, the first term of a sequence is 16. Each term of the sequence is half the preceding term, so dividing them by 2. Divide this by 2, divide by 2, divide by 2. So there's the first 4 terms. Let's fit those on one of these graphs. I wish I had my tall graphs for scaling purposes. But I'll scale these by going by 2s, which is fine for this set. So 20 and 10. So the first term's 16, 12, 14, 16. And then here's 8 and 4 and 2. This is clearly geometric, dividing by 2, common ratio being 1/2. Keep that in mind. They say half the previous term. So our recursive rule will be take half of the previous term, the first term being 16. For the explicit rule, we will take the first term times the common ratio to the n minus 1 power. And we don't have to really simplify that. They've been leaving it like that, so we will as well. Okay, number 37. The first term of a sequence is -1. Each term of the sequence is -3 times the preceding term. So this will change signs. Times -3 is +3. Times -3 is -9. Times -3 is +27. Like so. Probably easy enough to graph if I change my scales going by 3s, because these go by 3s all except for the -1, so that should be good enough for me. So this can be 30 and 15 and -15 and -30, like so. Because we got to have both there. -1 is a third of -3, so just a third of the way down like that. After that, we go by multiples of 3. That's a 3, 3, 6, 9. And then +27, which is 1 away from 30, like that. So there are the first 4. So far, the graphs have been okay, not super tall or anything like that. We have our recursive rule, where we take -3 times the previous term, starting from -1. And our explicit rule, the way that you'd actually write it here, we can write -1, but I'm just going to write the negative symbol You might see something like that. So opposite of, and then common ratio is -3 to the n minus 1 power. Do not try and simplify that and say opposite of -3 is +3, because order of operations still means you have to raise to this power first. Otherwise, if you turn it to +3, all of them would just be positive from there. And that's not the case. These change signs. And it starts negative. Number 38, last one of these. The first term of a sequence is 19. Each term of the sequence is 13 less than the preceding term. So we are going to subtract 13 from each thing here. I actually might have trouble. 19 minus 13 is 6. 6 minus 13, is -7. -7 minus 13 is -20. Okay, not too bad. I'll probably scale by 2s for this graph. Even though some hit odds, that's all right. So +20 and -20 we go, like so. Can't really see it. You're going to have to see it because we have to hit that point. So 19 is the first term, halfway between 18 and 20. And then 6 right on the button. -7, -2, -4, -6, -8, -7 here. And -20 right on the button here. Oh, too far over. So this is linear in nature. It's an arithmetic sequence. I can draw a line through it, though I will not. This has a recursive rule of taking the previous term and subtracting 13 from it, starting from 19. The explicit rule we will simplify. We are going to begin with our first term, and we'll subtract 13 n minus 1 times. If we distribute that -13, we're going to do 19 plus 13 to get what the 0th term would be, in essence, and that'll be 32. Here's the explicit rule. Okay, so we did both rules. We did the graphs. We are complete with those. All right, we're going to write a recursive rule and find the next two terms. Now, recursive rules are all about finding those next two terms anyway. I'll just write them in the list. I might find the next two terms first, in fact, given what we're doing. But 1, 3, oh, is this special? 1, 3, 4, 7, 11. Okay. I believe this one here. Okay, this is a special case here. Now, I was going to say common difference of 2, clearly not the case. What I think I'm seeing is something of the Fibonacci realm. It's just not exact Fibonacci sequence. But these two are adding to get this number. These two are adding to get this number. These two are adding to get this number here, right? So what I'm seeing is, maybe I should write the rule first. My rule looks to be, I'm adding the previous two terms before. So 2 terms before plus 1 term before gets me my next term. But I am starting with a first term of 1 and a second term of 3. It looks like I need to provide what both of those terms are to get the value of any of the other terms there. Now, a sub 6 is going to be 7 plus 11, which is 18. And a sub 7 is based off of those two previous terms, 11 plus 18, which is 29. So those are the next two terms in the sequence given what we're doing there. So I guess these are all special cases. We'll see if they probably all have that Fibonacci appearance. I don't want to be too caught off guard. So number 40, we have 10, 9, 1, 8, -7, 15. If I were to guess just based off the first two that I see, 10 minus 9 is 1. So let's see if that works out that way. I'll try and spell that out and see if that works. 10 minus 9 is 1. 9 minus 1 is 8. 1 minus 8 is -7, and 8 minus -7 is positive 15. That becomes 8 plus 7. So we got to do -7 minus 15 to get the next one. So we're taking one term minus the one before it. So a sub n takes the term before and subtracts, or 2 terms before, and subtracts the term right before that term. Boom, like that. Now your first term is 10, and your second term is 9. We do need the first 2 terms written out to work out what it is we're actually doing there. So to find the 1, 2, 3, 4, 5. So we already have 6 terms here. To find the 7th term, we got to do -7 minus 15, and that's -22. To find the 8th term, we'll take -15. 15. We'll take 15 minus -22. So it changes sign like that. It becomes 15 plus 22, which is 37. So -22 and 37. Not Fibonacci, but special. It's based on the same thing that Fibonacci does. 41 Okay, so 2, 4, 2, -2, -4, -2. Couldn't say off the top of my head. Let's see. 4 minus 2 is 2. 2 minus 4 is -2. -2 minus 2 is -4. I think it's this. I think it's this term minus that one. So 4 minus 2 is 2. 2 minus 4, I was thinking it's going to be geometric, but it can't by all the sign changes, is -2. So we're taking the term right before your next term, right? If I want to find the third term, I do the second term minus the first term. So this one is the second term is the term right before, and then minus the first term is the term 2 terms before, like that. The first term still being 2, and the second term being 4. So that appears to be this one, and it seems to follow suit. So that's the first 6 terms. The 7th term, we're going to have to take this one minus that one. So -2 minus -4, which is 2. We're probably going to repeat this set again. And the 8th term is taking well, let's see. Takes -2 minus -4. Now it's 2 minus -2, which is 2 plus 2, which is 4. So yeah, it looks like it's going to repeat it 2, 4, 2, etc. like that. Kind of goes back again. Number 42. I think this is just the addition of those 2 terms before it. So 6 plus 1. And I don't know if they're going to do any of them that are geometric in nature. I mean, I shouldn't call this arithmetic, but the fact that these are adding or subtracting, right, instead of multiplying or dividing. This looks to me, if you can tell, 6 plus 1 is 7, 1 plus 7 is 8, 7 plus 8 is 15. So it actually takes on Fibonacci nature over time. It just doesn't start from 1, 1 as the term. So the value of the next term, you take the value of the 2 terms before and add them together. So -2 plus the -1, like that. First term being 6, second term being 1. Okay, that's the first 6 terms. The 7th term is 15 plus 23, which is 38. And the 8th term is 23 plus 38. Oops. That should be 61. Okay. The next 2, I will just write out the lists despite what they are showing on the graph. So we have 1, 3. The third term is also 3. The fourth term is 9. The fifth term is 27. This doesn't look as arithmetic anymore, or, it doesn't look like we're adding anymore. It looks like we're doing some form of multiplication. In fact, to keep these as 3s, we're probably multiplying these. 1 times 3 is 3. 3 times 3 is 9. 3 times 9 is 27. And it looks like the product of our set. So to find the value of some next term, we're multiplying the 2 terms before. This term times this term. So they are showing up. The first term being 1, second term being 3. So these are very special cases. We are indicating what those first 2 terms are. So those are the first 5 terms. The 6th term is 9 times 27. 243. And now I have to do 27 times 243. I'm going to use the calculator here. Don't want to make a mistake. So I'm getting 6561. I think that's a perfect square of some number. I don't remember which one. I don't know. 81 squared. So 6,561. Okay, number 44, last one of that set. And we'll still have 15 more problems to do. We probably got to hit error analysis coming up after this set. So we start with 64, then we go down to 16, and then 4 and 4, and then 1. 64 divided by 16 is 4. 16 divided by 4 is 4. 4 divided by 4 is 1. And I mean, you could argue that I'm lucking out with that or whatever else. I mean, you're looking for what you're looking for, right? If you find it, it works out in that way. So I'm actually going to write this one as a division, not like multiplying by a fraction. To find some term, take the 1 2 terms before it and divide by the 1 1 term before it, like that. That's how I'm going to go about it. First term is 64. Second term is 16. So we have the first 5 terms. The 6th term is doing, well, 4 divided by 4 was 1. Now we got to do 4 divided by 1. So 4 divided by 1 is 4. And then we do, does this go back up? Let's see. No, now you do 1 divided by 4. 1 divided by 4 is 1/4. What happens after that? You do 1/4 divided by, 1 divided by 4. You do 4 divided by 1/4, and that's 16 again. So I guess it does kind of go up in its own way. Very strange kinds of sequences. I don't think these occur in nature, but interesting to see where they go from there. Number 45 and 46 are indeed error analysis. So describe and correct the error in writing an explicit rule for the recursive rule here. A sub 1 is 6, etc. So your first term is 6. Your common difference is negative 12. Looks like they put a positive 12 there. So you got to make it negative. I'm sure their math holds up, but they have the wrong insertion of that. Their common difference is negative 12 instead of positive 12. Now, they properly use the arithmetic sequence rule. That's what they were supposed to do. That's all good. They just have, there's a minus 12, so they should be using that. Now, the way that I tend to write this one, again, I write the, so first term and then the common difference next, because I like to distribute in front, not afterward. So, in distributing the negative 12, it's negative 12n plus 12 instead of positive 12n minus 12. And negative 12n, that becomes plus 18. So there's your fix for that one. All the rest is good for them. On number 46, we have, this looks like a special case thing of sorts, because they're doing, yeah, this is a special case. Now, looks like they treated it, see, they saw the first two, and I get it. They saw the first two and just assumed the pattern was plus 2 each time. But if you notice here, now it's plus 4 and then it's plus 6. So they're adding a different set from before. So this is not an arithmetic sequence. Despite the first two, the difference between the first two sets of terms, whatever, are common with 2. It changes afterward. This is a special case. So they said write the recursive rule. And yeah, these are very hard to come by with explicit rules. I don't know if I can come by them. They're a little trickier to talk about. This rule doesn't have a common difference. This looks like it's adding the 2 terms before. 2 plus 4 is 6. 4 plus 6 is 10. 6 plus 10 is 16. So we're taking the term 2 terms before plus the 1 term before. So your rule is first term 4, 2, second term is 4, like that. And I don't think we have to come up with any things afterward there. So they treated it as arithmetic. So this is a special case, not arithmetic. I think that's the big thing I have to call out, basically. I explained why it wasn't, but I need to catch their error. All right, numbers 47 to 51, the function f represents a sequence. Find the 2nd, 5th, and 10th terms of the sequence. Now, I did mention that, yes, you can use function notation on these. I don't want you to confuse it for multiplication, just like we did with explicit rules. So, f of 1 equals 3 means the value of the first term is 3. F of n, you take the term before it, f of n minus 1, plus 7. This looks to be arithmetic. It says the function represents a sequence. Find the 2nd, 5th, and 10th terms of the sequence. So here's what I'd probably like to do. I understand the second term is very easily done just by adding 7 once to it. And I can, right? The second term is 3 plus 7, right? Take the first term plus 7, you get 10. That one's good. The other ones, you might want to write out what the explicit rule is and plug in those numbers. I think that would just be more worth it to me personally. So this is an arithmetic sequence. You take the first term plus the common difference, n minus 1 times. And we can simplify that to 7n minus 7 or 7n minus 4. Maybe that takes more time than it's worth, but you can do it as an overall for these ones. So f of 5, the 5th term, is 7 times 5 minus 4. 35 minus 4 is 31. And the 10th term is 7 times 10 minus 4, which is 70 minus 4, or 66. So that's where those can come from. I'm kind of using a combination of both explicit rules and recursive rules to get those answers. I think that that's a nice way to spread those things out and work it that way. Number 48, your first term is -1, and this has a geometric sequence appearance. We're multiplying a common ratio of 6 to the previous term. So if I wanted to find the second term, I would do 6 times the previous term, -1, which is -6. This is one where, yeah, if I want to find the fifth term and stuff, let's go based off the recursive rule. We take the first term of -1 and multiply it by 6 to the n-1 power. So if I want to find the fifth term, I would do the opposite of 6 to the 5-1 power, or the fourth power. 6 to the fourth power is 1296, I think. So this is -1296. Remember, all these answers will be negative. Now, the 10th term, let's just write it over here. Kind of scattered appearance, I apologize for that. But the 10th term is the opposite of 6 to the 9th power, 10-1. Now, I'm going to use the calculator for that one, instead of writing out each term before it. And I think that can convince you, possibly, into saying there is good use for explicit rules here. So that number there, -10 million and something, something, something. All right, number 49. 49 will look a little tricky here, but I promise you it's probably going to be one of the easier versions of the answers. The first term is 8. And then take the previous term, and you're taking the opposite of the previous term, right? Basically multiply by -1. So f of 2 will be the opposite of 8, which is -8. Simple enough. Now these ones I don't really need to write the explicit rule for, because all you're doing is switching signs each time. I want to do this based off the oddness or evenness of the signs. The odd ones will be positive. The even ones will be negative. So this should be a +8 because you keep changing signs, right? And the 10th one is an even one, so that should be negative. So -8, +8, and -8 should be changing signs like that. The 100th term would be -8. The 951st term would be +8 because it depends on whether it's positive or negative. So they just keep changing signs. It's geometric, but they just keep changing signs. We got a special case here on number 50. So it looks like 51 is also a special case. So f of 1, this is one where we have to probably stay recursive, because I don't know how the explicit rule would pan out with this. So you take the second term plus, not the second term, the term 2 terms before plus the 1 term before. So they said find the second, fifth, and 10th terms of the sequence. We have the second term. The second term is 5. We're all done there. I'm just going to write out this thing as a list, literally, 4 and 5. So 4 plus 5 is 9. 5 plus 9 is 14. That's the fourth term. 9 plus 14 is 23. That's the fifth term. So second term, fifth term, and like I said, just keep going this way. 14 plus 23, 23 plus 37, 37 plus 60, 60 plus 97, and 97 plus 157. Like that. So this should be the second term, fifth term, and 10th term. I don't really have a better way of doing it than just that. So number 51, we take the difference of 2 terms. Now, we are doing f of n-1 minus f of n-2. That means we take the value of the term right before the one we're talking about, and then we subtract the one that's 2 terms before. So instead of doing 10 minus 15, I'm actually going to do 15 minus 10, and then proceed forward after that. So we do have the second term, but we're going to write it out as that list. I think that works out best. So 10 and 15. The third term is actually 15 minus 10. So that gives us 5. Fourth term is 5 minus 15. Fifth term is -10 minus 5. So it looks like this thing kind of repeats itself. Sort of. -15 minus 10 is -5. -5 minus -15 is +10. And I think this repeats itself here. So now we're going to 15, 5, and -10. If that thing seems to show the same pattern. Because we saw something like that before. So here's the second term. 3, 4, 5. Fifth term. And 6, 7, 8, 9, 10. Like so. Okay. Those were kind of fun. Number 52, modeling with mathematics. The X-ray shows the lengths in centimeters of bones in a human hand. Okay. Let's go. Wait, do we have that many? Do we have that extra knuckle thing? I don't know what that last one is. I don't think that's a human hand. Write a recursive rule for the lengths of the bones. Oh, interesting. So let's first write out what these things show, and let's see if we can figure it out. It's probably one of those special cases. I don't believe this is geometric. Maybe it is, but I don't believe it is. I think it's this minus this is that, this minus this is that, things like that. So yeah, this is a recursive rule. So for part A, looks like we're doing, and I'm going to use a sub n's again. A sub n, we take the value of the two terms before. Oh, did I do this last one right? Hold on. Was it two terms before or one term before that I wrote? Oh, good. I did do it right. Okay. All right. So we do the value of two terms before minus the value of one term before, like so. Now, your first term being 9.5 and your second term being 6. So here's your recursive rule. Part B, measure the lengths of different sections of your hand. Can the lengths be represented by recursively defined sequence? Explain. I don't have a ruler on me. I might have to skip this problem, guys. I'm looking around. I have a lot of stuff on my desk. I have like 100 rulers in my classroom. I don't have a ruler on me. I'm going to assume that's not true. I'm just going to assume that's not true. Not only that, I don't know how that last part's measured. That from the 3.5 to the 2.5, I'm looking at this as the... Oh, their first measurement is this guy right here. I see. That's going down to the wrist. So their first measurement is, say, this guy, and then that guy, and then that guy, and that guy. Maybe it is. I don't know. I'll have to skip. I apologize. I would need a ruler, but I don't necessarily believe that it's always going to follow that pattern. That would have to be pretty tricky to do so. So I'll just say prob's not. I could have ChatGPT come up with a human hand's lengths of those things, but I don't know which one's like the tarsal, metatarsal, and things like that. I think that's what they call them, unless I'm thinking of the wrist or something. I don't know. All right, number 53. You can use a spreadsheet to generate the terms of a sequence. Oh, yeah, totally. I use this stuff all the time. So, okay, they want us to do that. So let me pop up, I'm going to pause this. I'm going to pop up Google Sheets. Hold on a second. Okay, I have it prepped. And yes, I actually do this kind of stuff all the time here for different things I have to use for Google Sheets. Like, if I want to write these numbers, 1, 2, etc., instead of doing like 1, 2, 3, 4, you can actually just take the previous cell. I can do this one and then plus 1 to it. So you're always adding 1 from one to the next, and I can copy and paste that down. Boom, like that. And then boom, I have all the numbers. Now, what do they want us to do? Let me actually take a look. So we are going to generate the terms of the sequence here, you have to add 2. You do that. Okay, so use the fill down or copy and paste to do the first 10 terms. So I'm going to do that. I'm going to start with 3. Now I can take the previous term plus 2, and it's going to keep doing that each time. So I can copy paste or fill down for the first 10 terms like so. So we have that. Okay, so I did that. Use a spreadsheet to generate the first 10 terms of the sequence here for part B. And then, wait, am I supposed to write these answers? Let me, give me my old stuff. So let me write those down just to say we did it. Otherwise, I'll just say check, check, check. So the terms are 3, 5, 7, 9, 11, 13. And not say we couldn't do this on our own. But yes, these are done in that form. Part B, this one I might want to use this one. So the next one, it says use a spreadsheet to do this one. So we're multiplying by 4 each time. So I'm going to do it for, this is literally part B, column B. Have some of, so you hit equals and you take 4 times the previous term like so. And then we could duplicate that for the first 10 terms of this sequence. They get pretty big, right? So this is what we now have in this set. So I'm going to write these numbers down. Let me just write them down. Give me a second. 3, 12, 48. They get kind of big to write. I'm on the 8th term. 49152 19668. I don't know if I'm supposed to write them, but They did say come up with them, so good practice. Okay, part C, use a spreadsheet to generate the first 10 terms of the sequence where you do, your first term is 4, your second term is 7, and then you take the term before, like 7, and then subtract the one before. So with this one here, I'm going to take this minus that. Now, the way that this copies and pastes is basically like this. 3 minus 7 is negative 4, right? And this is what it's doing. It's now doing C3 minus C2. It's actually taking the 2 up above before that to do this. So I can copy and paste like so. Boom. And it looks like it has one of those repeated sets. There are different ways, because you might wonder, I don't know if you've done spreadsheets before, but there are some reasons that I might want to take just this 4 and do things with it over time. There are ways to lock it in place using actually a $sign, and I'm not going to talk about it here. But these are the numbers that I got to write for part C as this thing repeats itself. So yes, spreadsheets are really good for recursively defined sequences, such as these. Anything in programming you can do in recursively defined sequences as such. 4, 7, 3. So I haven't really seen a lot of these special case sequences like these ones done, but there they are. Okay, number 54. How do you see it? Oh, kind of Fibonacci-esque. Consider squares 1 through 6 in the diagram. 1, 2, 3, 4, 5, 6. What is the name of the sequence? What is the next term of the sequence? Well, this is Fibonacci sequence in that it's taking sums of values. It's kind of hard to explain how that thing works. But this is a Fibonacci sequence. Now, I'm trying to think how I would explain that. You may or may not know how the Fibonacci sequence works, but here is your 1, 1, and then, well, let's see. How does that work? Oh, okay, so this is 1, 1, and then the 1 plus 2 is 3. Let's see how that works. The 3, I forget how that works as far as making the sequence what it is. Because this whole thing is 2 right there. I don't know. I suddenly can't remember, but it is. But the next term of the sequence, you add up what you have before it. So the next one would be, let's see. So the first term is 1, second term is 1, third term would be 2. Oh, that's right. You're doing the squares of your numbers, 3. So this is like, it's a square. So 2 squared is 4, 3 squared is 9, things like that. So all we have to do is look at the lengths of these. So 2, 3, and then 5, and then 3 plus 5 is 8. So the length of this guy here is 8. 8. And then you have to do 5 plus 8, which is 13. And then 13 plus 8, which is 21. So those are the next. Oh, they just want the next term. Oh, I missed part A. I'm sorry. I was doing part B. Maybe it would have helped to do that one first for us to answer this question in the way that it is. So it says write a sequence in which this term is the side length of square n. If I saw that one, that would have totally worked itself out, right? So to find some term, you take the sum of the 2 terms before it. I know that because it's Fibonacci, but I also recognize that here because that's what we have. We have a side length of 1 here, and then a side length of 1, and then a side length of 2, side length of 3, etc. Now we do need to note the first 2 terms. A sub 1 is 2, and A sub 1 is 1, and A sub 2 is 1. Okay, part C, use the term in part B to add another square to the diagram and extend the spiral. So in this case here, I would basically take, I'm going to copy paste this thing. I would basically take what we have, and then extending the spiral, you can see it kind of connects the whole thing to make another square on top of what's already there. So here, I could basically make another square that does this. I'm not going to add the grid lines. No, it's not a square, I guess. It's a, yeah, I guess it is a square. It's a square like that. It's a little too big, but to extend the spiral, it would continue down, right here, like so. And it keeps spiraling about. So you can only see so much in the snapshot here, but it's going to be looking like that and spiraling outward. So that's how Fibonacci sequence works. And this 7, this is that length of 13. This goes 13 long like that. That's how I see it. All right, a few more questions. Questions, problems, or quablums. Number 55. Write the first 5 terms of the sequence here. Oh, interesting. So A sub 1 is 5. This is half arithmetic, half geometric. It's not really either. A sub n equals 3. times a sub n minus 1 plus 4. So we do multiply by 3 first, and then we add 4 to it. So the first 5 terms of the sequence. First term is 5. And then the next term we have to, well, here, let's write this actually more in full. A sub 2 is 3 times 5 plus 4. 15 plus 4 is 19. A sub 3 is 3 times 19 plus 4. That's 57 plus 4, which is 61. A sub 4 is 3 times 61 plus 4. 3 times 61 is 183 plus 4 is 187. And a sub 5 is 3 times 187 plus 4. That's 561 plus 4 is 565. So your sequence is 5, 19, 61, 187, 565, like so. Is that arithmetic, geometric, or neither? That's totally a neither. It doesn't have a common difference, doesn't have a common ratio. It features something where we multiply, but also something where we add, which means it's going to disrupt that flow. Explain my reasoning. Just no common difference nor common ratio. Does not have a common difference or common ratio. You are commonly doing something through addition and multiplication each time, but you're doing both. It's not an arithmetic geometric sequence, right? Number 56, we have Pascal's triangle. I don't know if we got to play with Pascal's triangle before. You will by the time you hit IM3, and this actually has some cool things to it. Describe the pattern for the numbers in Pascal's triangle shown below. Write a recursive rule that gives the mth number in the nth row. Oh boy. So Pascal's triangle does something where you actually add down these lists, like 1 plus 1 is 2, 1 plus 2 is 3, things like that. We can actually find those there. The ones go down the list like that as well. So that's something we can do. There are also other special things, but this is how I build Pascal's triangle personally. So you're adding down those things, but they say the mth number in the nth row. That's where things get a little confusing. So for example, this is actually, the nth row is technically considered, the first row is technically considered the 0th row whenever we actually do Pascal's triangle. So I'm wondering if that's how I should call it. This is going to be a little tricky. It is thought-provoking. So you are adding the two things before it, right? Now, when they say the mth number in the nth row, okay, I guess we'll call the first one the first row. Let's take a look at like this number, for example, right here, this 4, right? The 4 is the, well, let's use the 6 because I don't want to use the same number twice. 6 is the sum of this 3 and 3, right? 6, that's the third number in the 4th row. So the third number, oh boy. The third number in the 4th row takes the sum of the second and third numbers in the 3rd row. That's a lot to say. I think we have to have two different arrays here. If I have number and row, the third number in the 4th row takes the sum of the second number in the 3rd row and the third number in the 3rd row. And if I want to take another one like this, 5, that is the 5th number in the 5th row. So the 5th number in the 5th row takes the sum of the 4th and 5th numbers in the 4th row. The 4th number in the 4th row and the 5th number in the 4th row. Do we see a pattern? The 3 is the same here as the 5 is the same there. This is 1 less than the 3 and 1 less than that number there. So, okay, what I think I see here is the mth number in the nth row. I can do a sub m minus 1 comma n minus 1 plus a sub m comma n minus 1 like that. I think that's what we're doing there. Now I also need to note what the first number in the first row is. Oh gosh, how many different things do I have to mention? I'd have to mention the first number. Well, how about just this? Instead of the first number in the first row, let's just do the first number in any nth row. The first number in the nth row is 1, And the last number, the nth number in the nth row, is also 1. Because from there, it kind of goes on to that, and then we can use that each time to spell out the other ones. I think we can write it out like that. That one's really tricky. All right, number 57. The explicit rule a sub n equals da da da, that's the explicit rule, defines an arithmetic sequence. Okay, explain why a sub n minus 1, the value of the term before, is this whole number right here. So a sub n minus 1 equals a sub 1 plus n minus 1 minus 1 times d. Now, I like to write the d in front, but what I'm also going to do is a simplification of this thing. A sub 1 plus d times n minus 1 minus 1 is n minus 2. So what we're doing here is we're adding our common difference 2 less times, or 1 less time than the previous set. We add our common difference 2 less times than the term we're looking for, instead of 1 less time, because we're looking for the n minus 1 term, 1 term before the nth term. It's kind of tricky to write that thing out, but yeah, we're doing 1 less addition of the common difference. Instead of d times n minus 1, it's d times n minus 2. All right, justify each step in showing a recursive equation for this. All right, that's a lot of things to write there. Let's just do a copy paste of that. Okay, so this is still number 57. So that's part A. Part B. Okay, I'm really bad at writing justification steps here. So the first one, we're just writing the explicit rule. I don't know if we can say given. Given, or yeah, I'll just say given. Given that we have this, we're basically writing the equation down, right? Now from there, we're adding 0 to something, which means it's not going to change. I believe that's known as the identity property. Just keeping things as they were. I don't know why they're specifically doing it, right? They're showing that 0 is the cause of doing -1 plus 1. Now, given that -1 plus 1, those are additive inverses of each other. So I'll call it additive inverses. Again, I'm sorry if these are wrong. So what do they do from there? They grouped things differently. That's called the associative property, that you can group certain things to work them out. I don't know what they're going to do with that specifically. But the associative, how do you spell associative? Is it C? Associative property. What do they do from there? Do they distribute D and D? It looks like they use the distributive property there. Then they probably clean some things up. I can't tell where. Did they distribute more? They distribute again. Boom, boom. Let's see. What do they do from there? They turn this into a sub n minus 1. Oh, we probably use what we did before, right? If a sub n minus 1 equals this whole thing, notice this whole thing is right there. So that's a substitution. This thing took that guy's place. So substitution. I was like, what did they do? So it's actually based off of part A. Okay, tricky questions here at the end. I don't know if your teacher's assigning you these ones or if you're challenging yourself. Number 58. Your friend claims that the sequence cannot be represented by a recursive rule. Is your friend correct? Explain. Your friend is very incorrect because we literally had a question like this with the 8 and -8 and stuff like that. Very much so, this can be. This just needs a common ratio. So incorrect. I can dispute that by showing what the answer is. You can take your term before it and multiply by -1, or take the opposite of it. Just looks like that. And your a sub 1 is -5. Just take the opposite signs. Take the opposite signs. Number 59 says, write a recursive rule for this sequence here. So this sequence has 3, 7, 15, 31, 63. Well, it ain't 3 plus 7 or 3 times 7. I could do 3 times 5, which is 2 less than that, and 7 times... No, that's not going to work. I don't know this answer. if I take half of, if I do 3 plus, it might be one of those ones that was like number, maybe it's like this one here, number 55. You have a multiplication and an addition. And honestly, I don't know where to go from here to like determine what it is. I ain't too good at that. But it seems like one of those special cases. Like you got to use these two numbers to get the next one. Or actually, heck, let's just do this. Maybe I'm overthinking it. This is plus 4. This is plus 8. Oh, here we go. This is plus 16. And this is plus 32. Okay, I was overthinking it. I was trying to use two terms before. So we're adding double the amount that we did before. Okay, now that doesn't mean that we're fully done in what we have to write here. But your a sub n, we take the term before it, and we're adding not just 4, but 4, we're doubling what we were adding before. So for the second term, we add just one instance of 4. I probably have to put n minus 1 here. Let me kind of explain and show you that if this does work. I don't know if it will. This is both recursive and explicit at the same time, and I hope that that's still allowed to call that recursive, because this is what I'm thinking. So and the first term is 3. Now let's see if that actually does work out. In that, oh no, it's not just 4. You're not increasing by 4s. These are powers of 2. This is 2 squared. Let's do this again. This is 2 to the second power. I have to do n plus 1, I guess. The second power and the third power. Okay, let's try that. Let's see if this works. So a sub 2 would take a sub 1 plus 2 to the 1 plus 1 power, or 2 squared. That's 3 plus 4, which is 7. A sub 3 takes your 7, and it adds 2 to the third power. 2 plus 1 is 3. 7 plus 8 is 15. And the fourth term is 15. 15 plus 2 to the fourth power. See, we have to do all extra powers of 2. 15 plus 16, which is 31. And then, yeah, this seems to work out. A sub 5 is 31 plus 2 to the 5th, and 31 plus 32 is 63. So as long as we're allowed to use some form of explicit basis in this, then this is how this thing will work out. It's not based off the previous term at all, or the previous two terms. It's just based off the previous term as we do some extra work on it. So it looks like that'll be our answer right there that I boxed, and we should be good to go. You know, the second term, hold on a second. This is finding the second term. So I don't plug in 1 into here. I actually do plug in 2. So it actually should be just nth power, not n plus 1. So I apologize. The n plus 1 was by plugging in 1, but we're plugging in 2 into there. So I think it's just going to be 2 to the n. Now it follows what we're doing. That's a 2, that's a 2. That's a 3, that's a 3. Okay. I think that works out. All right, guys. That's the last problem, and that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and that concludes our chapter with regard to new material. Not everything there was exponential. Some things were. The last question actually literally had an exponent on it. But now we got to do the chapter review and the chapter test and cumulative assessment. So thank you guys so much. Take care. I'm going to see you in the next one.